All right, everyone. In this video, we're going to discuss signal integration, sometimes described as the integration ratio. I want to clarify that this is different from the Pascal's triangle ratio. The Pascal's triangle ratio was related to splitting. Now, the H1 NMR spectrometer will actually calculate the integration ratio, and what it does is it actually takes the area under each of the peaks for a given split signal. And the integration ratio is then calculated by the relative area under the peaks. Now, the way that you're going to see it is it would be the annotations in the spectrum, 1H, 6H, 2H, and so forth. That is the integration ratio. Now, the integration ratio is actually the relative number of hydrogens associated with each signal, emphasis on the relative number of hydrogens. Okay, that's different from the absolute number of hydrogens. So let's distinguish the relative, the integration, from the absolute. Looking at the structure, there's an overarching symmetry. And if you looked at all the protons of HA type, there's 12 of them. There's an absolute number of 12. For proton type B, there's 2 of them. That's the absolute number. Now, because of the overall symmetry in the molecule, the numbers 12 and 2 are both divisible by a common factor, aka the number 2. That gives us then a ratio. If we divide 12 by 2, we get 6. If we divide 2 by 2, we get 1. So the integration ratio for this molecule is 1 to 6. Okay. Now, that being said, if you were to look at, say, a molecule like this right here, notice there's no overarching symmetry. Because of that, what you would just do to determine the integration ratio is say that there's 3 hydrogens here, 2 here, 1 here, and the methyl groups would combine to 6. So the integration ratio is 1 to 2 to 3 to 6. List those numbers in increasing magnitude. Okay. So here the integration is the same as the absolute, but as we'll see for molecules with symmetry, the absolute number is going to be different from the integration. Before we get to that, if you ever see in a spectrum that you add up the integration values, 6 and 1 make 7, and that's a fraction of the total, that communicates that your structure should have some overarching symmetry. I'm going to repeat that. If you add the integration values up, and the total of the integrations is a fraction of the total in the molecular formula, there's some overarching symmetry to the molecule. If I take the total divided by the sum of the integration values, I get the number 2. Then if I multiplied the integration by 2, that would give me the absolute number associated with that signal, which is 2 hydrogens. If I take 2 times 6, that would give me 12 hydrogens. That's the total absolute number of hydrogens associated with that signal. Okay? Now, on your exam, you might have to calculate the integration ratio again if there's no overall symmetry. You just count the number of hydrogens at each position and then list those numbers in increasing order. Now, I've done some work ahead of time here and I've colored in proton sets. You'll notice that the far left molecule is symmetrical about this line. That means the methyl groups are equivalent, colored in blue here, totaling up to 6 hydrogens. The red hydrogens are equivalent, totaling up to 2 hydrogens. And the gray hydrogens are equivalent, totaling up to 2. Now that's the absolute number, and because of the symmetry, each of those is divisible by 2. So the integration ratio becomes 1 to 1 to 3. In other words, 6 divided by 2 is 3, 2 divided by 2 is 1, 2 divided by 2 is 1. Okay, and that's what I'd recommend that you do is you mark the protons that are equivalent, write the absolute number, and you do that for each of them. And then if there's overall symmetry, you divide by the common factor, which here is the number 2. For example B, I marked that all these methyl groups are equivalent, totaling up to a total of 12 absolute hydrogens. Then I've got these 2 hydrogens here, which are equivalent, totaling up to 2. Because of the overall symmetry and the fact that they're divisible by a common factor, I divide each by the number 2, and that would give me a 1 to 6 integration ratio. Looking at example D in the bottom left here, again, I've labeled stuff ahead of time. The methyl groups are equivalent, totaling up to 6, 2 and 2 totaling up to 4. And because this group is the same as this group, all the protons of the ring are equivalent, totaling up to 4. Because of that symmetry, we can divide. 4 divided by 2 is 2, 4 divided by 2 is 2, and 6 divided by 2 is 3. 2 to 2 to 3 integration ratio. Looking at the next structure, the methyl groups are equivalent, totaling up to 6 H's. Red hydrogens are equivalent, totaling up to 4. Gray hydrogens are equivalent, totaling up to 2. 2 divided by 2 is 1. 4 divided by 2 is 2. 6 divided by 2 is 3. 1 to 2 to 3 integration ratio. And finally, looking at the far right structure, there's a symmetry about this line here. All the methyl groups are equivalent, totaling up to 12 hydrogens. We have the red hydrogen here and the red hydrogen here equivalent, totaling up to 2. The gray hydrogens total up to give me 4. 2 divided by 2 is 1, 4 divided by 2 is 2, and 12 divided by 2 is 6. So those are the values that I've indicated in the boxes are the integration ratios. Again, the values that I've put up here would be the absolute number. And if there's overarching symmetry, as we had in these structures here, then we divide by the common factor. And usually that's the number 2. In other instances, it could be the number 3. Find the common denominator and divide by that. So in recent semesters, if you have any questions like this, definitely be prepared to solve a question like this. And understand that if in the spectrum you add up the integration values and it gives you a fraction of the total, that means that there's some overarching symmetry. And for molecules where there is no symmetry in the spectrum, you'd see, 3H, 2H, 1H, and 6H. If all of those numbers add up to give you the total, the absolute is the same as the total, then each of those is indicative of the legitimate number of hydrogens. The absolute is equal to the integration value. Okay, so take whatever time you need to fully digest this, but it's important to be able to calculate the integration ratio, which again is different from the Pascal's triangle ratio, which is related to splitting.